In this video, we're going to do some extra examples involving conditional probability and independent events. So let's start with this example here. So after the most recent set of sunny days, 75 motorists that were involved in automobile accidents were surveyed about whether or not the accident was their fault and what type of tires they had. Okay, and the findings are summarized here. So again, this is giving the intersections. So for instance, 22 means that there was 22 people who were at fault with all season tires on their car. So we're going to select one motorist from random from this group of 75. And the first thing we want to know is, what is the probability that the selected motorist was at fault for the accident and had summer tires? So I'm going to say let F be the event that they were at fault, and maybe T is the event that they had summer tires already. Okay, so what we're looking for here then is the probability that they were at fault and had summer tires. So that's F intersect T. Now, because we're picking one motorist at random from the study, this is going to be a uniform sample space. So this is going to be the number of people who were at fault with summer tires divided by the number in the sample space. So we just need to look at the table here. So at fault with summer tires, that's 20, and there was 75 in total. So this is going to be 20 over 75, which is actually 4 over 15. Or if you prefer decimals, it's approximately 0.2667. Okay, now the next part wants to know the probability the selected motorist was at fault. Okay, we don't care what type of tires. So this is the probability of just F. Okay, so the number of people who were at fault divided by the number in the sample space. So we know the bottom is 75. The number of people at fault, we want to just add up the number in this row. So that's 8 and 22 is 30, plus 20 is 50 in total. So this is going to be 50 over 75, which is 2 over 3, which, if you prefer decimals, is approximately 0.6667. Now we're getting into some conditional probability. So given that, we know something's happening. Given that the selected motorist was at fault, what's the probability they had summer tires? So we're looking for the probability they had summer tires given that they were at fault. So T given F. So using the formula, okay, and we have a uniform sample space, so we can go right to the number if you'd like. This is the number in the intersection divided by the number that were at fault. So the number in the intersection was 20, and there were 50 people at fault. So this is going to be 20 divided by 50, or 2 divided by 5, which is 0.4. Okay, so are the events chosen motorist was at fault? So this is event F. And chosen motorist had summer tires, so this is event T. Are they mutually exclusive? So remember, mutually exclusive means they cannot happen at the same time. So they cannot occur together. So we know here that they're not. Okay, so not mutually exclusive. Since we already computed the probability of their intersection, so the probability of F intersect T we found was 4 over 15, okay, which is not 0. Okay, if they were mutually exclusive, their intersection probability would have to be 0. So it would be impossible for them to occur at the same time. Now, are these events independent? Okay, so this is a tougher question to answer. So we need to check that they're independent. So what we want, I'm going to do it with the, maybe I'll just write the formula here. So if independent, then we should have the probability of F times the probability of T is equal to the probability of F intersect T. Okay, so that's what we're going to check. So we first compute the probability of F. We actually already did that. So that's 2/3. Okay, now if we compute the probability of T, it's the number of people in T divided by the number in sample space. So how many people had summer tires? That's 30. 30 over 75, which is 2/5, or 0.4 if you prefer. And we already know the intersection was 4 over 15. So what we want to do is take probability of F times the probability of T. So that's 2 over 3 times 2 over 5. And we get 4 over 15, which is the probability of the intersection. Okay, so that means that these are independent. Okay, another way we could have checked, okay, which is maybe a bit faster here because we already computed the probability of T given F to be 2 over 5. Okay, so what we would need to check if this probability is equal to probability of just T, okay, which we found here was 2/5. Okay, so because they're equal, they're also independent. So since equal, these are independent. Both ways are fine. Okay, I normally do the purple way most often, but when you've already computed some conditional probability for the events, then sometimes it's faster to use one of the other ways, but whichever way you like is fine. So let's try another one. So a family of 3, Ksenia, Katya, and Dave, they're going to get a family photo. The photographer will only take one photo, and the family knows on one photo that the probabilities for a good photo for each of them, so Ksenia, Katya, and Dave, are 0.6, 0.9, and 0.3 respectively. Okay, so I'm going to say that KS is Ksenia photo is good. Okay, KA is Katya's photo is good. Oops. Okay, and D can be Dave's photo is good. Okay, so then they gave us probability of KS is 0.6, probability of KA is 0.9, and the probability of D is 0.3. So that's what we know. And they also tell us this extra piece of information: assume the chances of each of them having a good photo are independent from one another. Okay, so you know that they're independent. So what is the probability they are all able to take a photo in which they're able to take a photo where all 3 of them have a good photo? So what we're looking for here is the probability of KS and KA and D. They're all good. Now, since they're independent, this intersection is actually easy to compute. So because they're independent, we know that this intersection probability is just the product of the 3 events happening. So it's the probability Ksenia has a good photo times the probability Katya has a good photo times the probability Dave has a good photo. So it's going to be 0.6 times 0.9 times 0.3, which is 0.162. Now, if you know at least one of them did not have a good photo, what's the probability that Dave is the only one that didn't? Okay, so what we're looking for here is probability only D complement given at least one bad. Okay, so only Dave is bad given that at least one of them is bad. So we use our conditional probability formula. So that says only Dave is bad and at least one is bad, divided by the probability that at least one is bad. Now, for the intersection, we have at least one is bad and only Dave is bad. Okay, so if only Dave is bad, that means at least one is bad. Okay, and if at least one is bad, it could be Dave or Ksenia or Katya or multiple. So the intersection here is actually just the more specific one, which is only Dave is bad. So maybe, yeah. And then if we want to compute the probability at least one of them is bad, it's probably easier to use the complement and do 1 minus the probability that they're all good, which is actually what we computed up above. Okay, so this is going to be the probability D complement. So Dave is bad, but Ksenia is good and Katya is good. And then we're going to have 1 minus part A. So we already computed this. Okay, now again, since they're independent, this intersection probability can be computed with multiplication. Okay, so it's the probability Dave is bad times the probability Ksenia is good times the probability Katya is good. And the bottom here is going to be 0.838. So Dave not having a good photo is 1 minus 0.3, so that's 0.7. Ksenia having a good photo is 0.6, and Katya having a good photo is 0.9. So you end up, if you compute that, with 0.378 over 0.838, which is approximately 0.451. So there's a 45% chance that Dave is the only one with a bad photo, if at least one of them has a bad photo. Okay, but again, maybe I should write here, this equals is since they're independent. We're allowed to do that. Okay, so them telling us that they were independent was actually very useful. Okay, so they're independent of one another. So one having a bad photo doesn't affect the chances of the other one having a bad photo. Okay, let's try another one. When a pair of dice is rolled, what's the probability the sum of the two dice is 8, given that you know the sum is not 7? So here's another conditional probability. So this is this. We want the probability the sum is 8 if we know the sum is not 7. So using our conditional formula, this is the probability the sum is 8 and the sum is not 7, divided by the probability the sum is not 7. Now, if we think about this intersection, when could both of these happen? Well, we need the sum to be 8 in order for the sum to be 8. And if the sum is 8, then it's definitely not 7. So I should put a tick mark there. Okay, so the intersection happens precisely when the sum is 8 on the two dice. And when we want the probability the sum is not 7, it's probably easier to do the probability 1 minus the probability when the sum is 7. So now we just need to compute these probabilities. So when we roll two dice, we know that the number in the sample space is 6 times 6, so 36. Okay, the number with the sum equals 8 is actually 5. So maybe I'll write these ones out. So you can't have 1 with anything, but you can have 2 with 6 or 6 with 2. You could have 3 with 5 or 5 with 3, or you could have 4 and 4 together. Okay, so that's why you get 5 there. So the top is going to be 5 over 36. Okay, now when you have the sum equals 7, I'm just going to write it here because I'm running out of room, but you have 6 over 36. So I encourage you to write down all 6 of them so that you know that there in fact are 6. So if you compute this, your calculator can do this for you even with the fractions. you should get 1 over 6, which is approximately 0.1667. Okay, one more. So, suppose I have 12 pairs of gardening gloves in a bag in my shed. When I go out to the garden, I reach in and I randomly select 4 gloves, 4 individual gloves. What is the probability that I select exactly 2 pairs, given that I know I'm going to get at least 1 pair? Okay, so I want the probability of exactly 2 pairs, given at least 1 pair. So my first thing I always do is to write the conditional formula. So this is exactly 2 pairs and at least 1 pair divided by the probability of at least 1 pair. Now, when does the intersection happen? Well, if I get exactly 2 pairs, I got at least 1 pair, but I have to get exactly 2 pairs. Okay, so the intersection is actually just the probability that I get exactly 2 pairs. And then to compute the probability of at least 1 pair, I'm going to do 1 minus the probability of no pairs. Okay, but you could do the cases if you want. There's only 2. So now I need to count this. So I'm going to have 1 minus on the bottom. So what's my sample space? So I have 12 pairs of gardening gloves. That's 24 gloves. And I'm going to reach in and grab 4. So my sample space is going to be 24, choose 4. Okay, so I know that I'm going to divide these guys by 24, choose 4. Okay, now when I am counting these, remember that they come in pairs. 2, 3, 11, 12. Okay, I got all 12 of them. They come in pairs. So if I want no pairs, then I want to pick 1 glove from each of 4 different pairs. So I'm doing the bottom one first. So what I'm going to do, because it's 1 glove each, I want to select from the 12 types 4 different types. Now it tells me the left and right gloves are distinct, so I know I can tell them apart. So I want to know if I get the right or the left one. So for each of these chosen kinds, I need to pick the right or the left glove. So I'm going to do 2, choose 1, 4 times, so to the power 4. Okay, now if I want to get exactly 2 pairs, that means that I want both of this kind and maybe both of this kind. So what I want to do here is select 2 kinds. So from the 12, select 2 kinds. And then for each of those kinds, I'm going to take both their shoes. So I'm going to do 2, choose 2 squared. Two choose 2 is a 1 though, so you don't actually really need that. Now we could have done, because the sample space is uniform, we could have done this with just counting, but then the 1 would have had to change to a 24, choose 4. Okay, so the top probability is going to be 0.0062-ish, maybe 621. And then I have to do 1 minus 12, choose 4, 2, choose 1 to the power 4, divided by 24, choose 4. So on the bottom, I'm going to have 0.25466 approximately, which when I divide these two, when I divide these, I'm going to get 0.0